Hellish months we waste away waiting for this to go live. Okay. Titrations. Titrations are one of the most powerful tools that we have in chemistry. And being able to find the concentration of a solution is the least of it. Okay, titration, you can, because of our ability to very precisely control concentrations and volumes, we can find out a heck of a lot, especially if we measure other things at the same time, like pH. Measuring pH of a solution while we slowly add another solution to it, we can figure out a lot about an acid or a base. The way we do that is we use a solution where we know the concentration. We know it incredibly well. And so, like I said, burettes, wonderful for this, for delivering a known concentration and a very well-calibrated volume. Because these things, like I said, you can deliver drop by drop, or even a half drop if you ever mind. And then you have the thing down below where you're trying to analyze it. You want to know what the concentration is. And so you just add a little bit of your known thing to the thing that you don't know, the thing that you want to know more about. You mix them together, and you wait until you've reached what's known as equivalence, when the stuff you're adding has perfectly reacted with the stuff you're analyzing. Now, we call it equivalence because it's not a one-to-one relationship. So it's not equal amounts, it's equivalent amounts. Okay, so like in the previous reaction, at the end of the previous thing, sodium hydroxide reacts in a 2-to-1 ratio with sulfuric acid. So if you want to completely react sodium hydroxide with sulfuric acid, you need twice as many moles of sodium hydroxide as you do sulfuric acid. Hydrogen peroxide, meanwhile, reacts in a 5-to-2 relationship with permanganate. Okay, so you need 5 times as much of this. So the point is, we're saying that once the reaction has been perfectly equivalent, not equal, equivalent, that's when your reaction is done. So we use these words pretty carefully. Science has its particular vocabulary. So equivalent amounts, mole to mole equivalents. So 2-to-1 for this reaction, 5-to-2 for this reaction. Some reactions, it could be 1-to-1, such as sodium hydroxide with hydrochloric acid. That would be 1-to-1. But sodium hydroxide and sulfuric acid is 2-to-1 because this guy just releases 2 of those acidic protons. So sometimes finding equivalence is easy, or easier with technology. For example, here we have a solution of some base, a strong base, so probably sodium hydroxide or potassium hydroxide. So we're starting at this really high pH, really, really basic, and we're adding some sort of acid to it. And as we do that, the pH gets lower and lower and lower and lower and lower, and then boom, it just plummets as we just abruptly run out of base, and suddenly, because we've been adding acid this whole time, now we're down here at a low pH. So the equivalence is when we see this massive drop in pH. So that's what we call the equivalence point, when we get this inflection going, okay. But once upon a time, it was a little bit harder because they didn't have electronic pH probes. We have those now, and it makes things a lot easier. But once upon a time, they had to use an indicator. An indicator was a dye, and dyes are often weak acids or weak bases themselves, so they change color in response to a change in pH. So here we have the indicator methyl violet. At a very low pH, it is this sort of pale yellowish color. At a less low pH, so pH 4, still acidic, it is now a violet color. So a lot of indicators change pH at they change their pH, they change color, I should say, at different pHs. So by choosing what indicator you're using, you can figure out a little bit better where the equivalence point occurs if you know what pH the equivalence happens at. In this case, because we're using a strong base, the equivalence will happen at a pH of 7. But not all acids and bases are strong acids and bases. We'll get into that more later. But here we have sodium hydroxide and hydrochloric acid. What is the concentration of a 15 milliliter solution of sodium hydroxide if it reaches equivalence after the addition of 12.755 mils of a 0.125 molar hydrochloric acid solution? So this is a very typical sort of titration. Okay, we have 15 mil. We know it's a sodium hydroxide solution, and we know how much of it we have. We just don't know its concentration. And then we have this well-characterized hydrochloric acid solution. We know what its concentration is. And then we slowly, do something like this, where we have, our base solution, and we just add slowly over time some hydrochloric acid until we see the equivalence happen. Okay, that's all we're doing. So thanks to having a burette, we have a very, very precise measure of the volume of hydrochloric acid that we added. So the sodium hydroxide, it reached equivalence. It was perfectly neutralized, or as perfectly as we could measure, after we added 12.755 mils of our well-known, well-characterized 0.12500 molar hydrochloric acid solution. So what is the concentration of this sodium hydroxide? Well, we need a balanced reaction, and I'm being kind of tricksy about this. This is already balanced. It's 1 to 1 to 1 to 1. Okay, so we're starting off easy here, which means that at equivalence, the number of moles of hydrochloric acid is exactly equal to the number of moles of sodium hydroxide. Okay, so just makes it a little bit simpler. Okay, so let's bring this up. So we have 0.12500 molar HCl. Okay, so molar means moles per liter. Oh, you can barely get there. We go. So we also had a certain volume of that. Remember, we have to convert to liters. So we have 12.755 mils. Move the decimal place 3 to the left. 0.012755 liters. So that means that when we did this titration, okay, going back to previous slide, okay, we had our hydrochloric acid up here in this burette. We had our sodium hydroxide. Hey, Wesley pup. We had our sodium hydroxide down here in this flask. And we added, bit by bit, the 12.755, you feeling needy, buddy? 12.755 mils of our hydrochloric acid. Okay, and we watched carefully our sodium hydroxide down below and waited for it to be neutral. Maybe we had a pH probe, maybe we used a nice indicator. Regardless, we were able to measure that very, very carefully because we're smart. We're wicked smart. So this is how many moles of hydrochloric acid we added. Okay, let me bring up my calculator. Let's hope my dog decides not to bump into too much stuff. 0.125 times 0.012755 means that we added 0.0015944 moles of HCl added. Okay, so we added that many moles of HCl, and because it's a nice straightforward equivalence, that means that that's how many moles of NaOH were in the thing to start with. Okay. By the time we've added this, it's all been used up, but that's not what we care about. We're using this to figure out what it was like at the start. Okay. So we added this much, so how much sodium hydroxide must there have been in it when we started? So 0.0015944 moles of HCl times 1 mole of NaOH for every 1 mole of HCl. Okay. Every mole of HCl that we reacted was used to neutralize 1 mole of NaOH. Meaning, because it's a nice straightforward 1-to-1, it's the same number of moles of NaOH. But here's another reason that we talk about equivalence rather than equality. Because, coming back to the thing, we didn't have the same volumes. We started with 15 mils of our unknown concentration of sodium hydroxide. We added a different volume of HCl. Okay. So we work with volumes, but we have to, but what we care about in the end is moles. And it's not always going to be equal numbers of moles, but equivalent numbers of moles. So, all right. So now that we have our moles of sodium hydroxide, what's our concentration? Well, that's just the 0.0015944 moles of NaOH divided by the 0.015000 liters. Remember, although I gave you the volume in mils, you have to work in liters when you're doing conversions back and forth with molarity. So 0.0015944 divided by 0.015. Yes. Gets us a concentration of 0.10629 molar NaOH. So just to help you build up a little bit of intuition about this, does this make sense? This is a lower concentration, 0.125 to 0.1062. Okay. Yeah, that makes sense because we took a smaller volume of the acid to counteract the base. So it takes less acid. The acid must have a higher concentration. More base means it has a lower concentration. All right, so maybe that will help a little bit with that. So now let's look at a different base and a different acid, specifically potassium hydroxide and sulfuric acid. All right. So once again, we're dealing with a well-characterized acid, 0.87500 molar sulfuric acid. And we know very, very carefully, very precisely, how much of that acid we added, 17.578 mils. And we know very well how much of the base we started with, but we don't know its concentration. Now, in this case, it's not a one-to-one reaction. Sulfuric acid is what's known as a diprotic acid. It has two acidic protons over here. So it will react with twice as much potassium hydroxide. And that'll matter. That'll make a pretty significant difference. So first, well, I'll just go ahead and write out the balanced reaction. We're going to need 2 potassium hydroxides for every 1 H2SO4 in order to neutralize it to get potassium sulfate and water. Okay. So that's, again, just stressing why we call it equivalence, not equality. But again, after that, it's a Stoich problem. We have 0.87500 molar, so molarity is moles per liter of our H2SO4. And again, I'm going to keep on hammering this home because I can, and you can't stop me. This is mils, but molarity works in liters, so we have to convert to liters. 0.017578 liters of H2SO4. Zero 0.01538. Okay, you're not doing anything noisy. You're just breathing. Moles of H2SO4. All right. So now, given that, how many moles of potassium hydroxide? Okay. For every 1 mole of H2SO4, there must have been 2 moles of potassium hydroxide. It's a 2-to-1 ratio. Okay. So 0.015381 moles of H2SO4 times 2 moles of KOH for every 1 mole of H2SO4. This is just a standard Stoich step, a perfectly standard, absolutely normal Stoich step. All we've done is convert to moles of our substance A. Now we're converting to moles of substance B. Okay. Okay, so now we know how many moles of KOH were in that solution that we started with. Okay. So, knowing moles, we also know, thankfully, our volume because we measured it before we started our titration. We know we started with 25 mils of the potassium hydroxide. So it's just going to be, I'm going to switch colors again. Got to keep it fun for myself somehow. 0.030762 moles of KOH divided by 25 mils is 0.025000 liters of our potassium hydroxide. Meaning that our original solution of potassium hydroxide was 1.2305 molar. So that would have been pretty gosh darn concentrated. All right. So that is yet another example of a titration. Okay? So we can do more than just find concentrations, but that's all you'll be able to do right now because you just haven't learned quite enough chemistry. But it works for more than just acids and bases. So for example, this here is a reaction between potassium hydroxide, hydrogen peroxide and potassium permanganate. This is a class of reactions you'll learn more about later on. And they are weird to balance. So I went ahead and balanced it for you without leaving the blanks. So if we have 10 mils of hydrogen peroxide, and then we add, again, a well-characterized solution of potassium permanganate. What is the concentration of our hydrogen peroxide? Okay. So I'm not going to write out the equation this time because I don't have to. Now, for reasons that, well, potassium permanganate is purple, so I'm going to start off in purple on this one. All right, so we have a 0.12000 moles of KMnO4 per liter of KMnO4 because that's the concentration. And we had 0.011482 liters of our potassium permanganate. What is the moles of potassium permanganate? 0.12 times 0.011482. 0.0013778 moles of potassium permanganate. All right. And it was reacting with hydrogen peroxide. For hydrogen peroxide, I'm going to go ahead and use orange because it's dangerous, but it's not an acid. It's a totally different kind of dangerous. So we convert that standard stoich balanced chemical reaction, 5 moles of hydrogen peroxide for every 2 moles of potassium permanganate. So equivalence is a 5-to-2 relationship in this case. So our hydrogen peroxide, we started out with 0.0034446 moles of H2O2, and that 0.003446 moles of H2O2 was contained in 10 milliliters, or 0.010000 liters. Hopefully my dog and cat playing in the background is not too noisy, meaning that this solution was 0.34446 molar hydrogen peroxide. All right. So those are titrations. They really do boil down to being that simple. It's just a specific example of a kind of solution stoichiometry. It's one that is incredibly popular because, like I said, once you have other measuring tools in the mix, you can discover some really deep juju related to different materials. You can discover the strength of acids and bases. You can discover the chemical activity, which is something that you don't even really cover until like grad school. There's a lot of stuff that you can do that comes down to just your ability to measure. And titration is one of those basic tools that has turned out to have a lot of analytical power behind it. Okay. And with that, we are done with titrations, meaning we are done with Chapter 6. And I will see you tomorrow night for Chapter 7. See you then. I'm going to